your notes, and so let's start talking about this. You're going to find that this is very similar to everything that we've already done. It's going to lead you down the exact same path. Just going to kind of solidify a few differences to make sure that it's going to even strengthen what you have already done for this. All right. So we are going to be doing an inference about two separate averages. Okay, so I'm emphasizing that we have two separate groups because tomorrow that will not be the case. All right, so we know that we always have to check our conditions first, so let's just see how that works for us on these, see if there's any differences. You do have to do the conditions for both groups. Okay, you do need to make sure you are doing them for both groups. So that means you either address both groups whenever you do them, or you do two separate lists. I typically don't like to do two separate lists. I just kind of address them all in one list at the same time. So make sure that when you talk about being stated or assumed random, that you say for both groups. Okay, make sure you are notating that you are referencing both groups. Now, for the sample being less than 10% of the population for both groups, this means you're going to have to write these out separately because you're going to have two separate populations. So, you will have to be writing these out separately because you have two populations, the population that the first group comes from and the population that the second group comes from. So that will be looking like two lines. And then also, whenever you have two groups, we saw this with two proportions. So this is also with two means. You have to make sure that the groups are independent of each other. For example, if I was doing an average shoe size for the males and an average shoe size for the females, then I have to make sure that there's not any person in both of those groups, that I'm getting the data and it's mixed in both of those groups. Those two averages cannot have same subjects. Okay, now, large enough is the same as we have been doing, same as we did in chapter 23. The key is you have to do this for both groups. So in order to be large enough, they both have to have a sample size greater than or equal to 30. If they are not greater than or equal to 30, then what could help you out there and get you past that problem? They tell you that the parent population is normal. Okay? And then, here's the problem. This is really annoying, but you may have to draw two histograms if the samples are not large enough and they do not tell you that the parent population is normal. Just like you did on quiz 23, and you might have something that looks like this. This is the first problem on the homework, where you have a sample of fish from Buy Right Pets, and you have a sample of fish from Fish Friends, and those are not large enough. And I don't think that we have information in the problem that they are approximately normal for the population. So you are going to have to make a histogram for Buy Right Pets and a histogram for Fish Friends. Annoying, I know, but necessary, because you have to make sure that that it is unimodal. Remember, whenever you're doing a histogram, you're checking that it's unimodal. What else are you checking? Somewhat symmetric. And that there are no outliers. Because basically, here's what we're saying. When we draw a histogram and it has these qualities, we then are inferring that the population must be pretty okay, so let's go with it. That's what's happening. When we identify these qualities in a histogram, we say, oh, the population must be pretty okay if our sample looks pretty okay, so let's go with it. All right, so that's what's happening there. Now, we are going to get, oh yeah, and by the way, our conclusion is nearly normal model applies. Now, on the quiz 23s, I actually got some people putting nearly in the wrong place. I got some people saying normal model nearly applies. Okay, so that's no good. You can't say the normal model almost happens. You say the almost normal model is happening. Okay, I know that's a little subtle difference, but this is the correct way. Additionally, here's the critical thing. There is just one normal model. This is a normal model because we are going to be interested in the difference in the two averages. Okay? We're going to be taking the average of group 1 and subtracting the average of group 2. And that will become one number inside our curve. And then somebody else's one number inside our curve. Somebody else will get two averages, subtract them, and get one number. Somebody else will get two averages, subtract them, and get one number. Okay, so you have one normal curve made up of the difference between those two averages. Okay, let's skip this part about pulling. We'll come back to it shortly when we do the calculator work, but let's go to our example. So here we go. All right, before we start, well, no, we'll talk about the problem first, and then I'll mention this. Okay, a dietitian has developed a diet that is low in fats, carbohydrates, and cholesterol. Although the diet was initially intended to be used by people with heart disease, the dietitian wishes to examine the effect this diet has on the weights of obese people. Two random samples of 100 obese people are each are selected. One group of 100 is placed on the low-fat diet, and the other group of 100 is on a diet that contains approximately the same quantity of food, but is not as low in fats, carbohydrates, and cholesterol. Actually, the thing I get excited about when I read that sentence is that both of these samples are of 100, and so my brain's thinking what? It's going to be large enough, and I'm just like going, yes, I'm not going to have to draw a histogram. Plus, based on this data, you know, I couldn't draw a histogram anyway because I have to have all those little individual numbers. So, anyway, just FYI. All right, each person, the amount of the weight lost or gained in a 3-week period is recorded, and then here are the results. So what we have is the sample mean, and we have the sample variance. Dun, dun, dun. I missed this for 2 class periods. I just kept jumping that this was the standard deviation. It's not, according to this. You need to remember to pay attention. Since this says it's the sample variance, technically, what are we supposed to do to get the standard deviation? Square root. Correct. However, for teaching purposes, I actually like the results I get as if this was the standard deviation. So let's just pretend that this said standard deviation and leave it at that. I like that better because you'll see later for teaching purposes there's actually a really good result that comes out of this to demonstrate something for you. Okay. All right, so see, this would be the mean, the sample mean. Do you see how I notate it with X bar for the low-fat diet? And this would be the sample mean for the 100 on the not. I'm going to do N for the not low-fat diet. So this is the standard deviation for the low-fat and the standard deviation for the not low-fat. All right. So today, what parameters are we going to be defining? Parameter means what population are we going to take these samples and infer to? Okay. We're going to be inferring to all obese people that are on the low-fat diet. And what number are we going to be getting from that? What will this mu, see now it's a mu with an L. Good. It will be the average weight loss. And you are inferring to a population. So this is going to come out to tell you about average weight loss of all the obese people on this low-fat diet. Okay, so all obese people that do this low-fat diet will average here what you're inferencing or have this approximation. Low-fat diet. Okay, and then I have a mu for my not low-fat diet. So that's going to be the same thing, but it's on the not low-fat diet. So average weight loss of all. I like to emphasize that I am going to make an inference about the population from my one little sample. That's big. All obese people on, yeah, not on the low-fat diet. Yep. I typically, just FYI, I don't like to use O's. I don't like to use O's and S's because those sometimes look like zeros and fives and stuff. Yes. I think that that's probably a good point. I think that's a good point because this other diet, remember, they specified that it is approximately the same quantity, but not as low in fats, carbohydrates, and cholesterol. So probably better stated would be the other diet. True.
Do a D instead for diet instead of N for not.
I don't know. So anyway, probably a good point to say other diet. I'll probably give you a stamp for that one. That's a good thing to consider. But I'm going to use N still just because I'm creature of habit and already have. Okay, so here we go. Assumptions, our favorite thing. What are we going to start with? Okay, random. What does it say? It is stated, and if you just put that right there, it's wrong. Because it is stated for both groups. I should say it's incomplete. Okay, stated for both groups. Okay, independent. All right, we need to reference both groups on this. So the first 100 is less than 10% of what population? Yeah, all obese people on low-fat diet. That's the first population. Okay? And then 100 is the second sample of 100. These are separate. You're not saying 200 is less than blah, blah, blah. No. You're separating them out because you have to make sure each sample is sufficient. 10% of what population? Yep. All obese people on the other diet. Okay? All right. And because I have two items, what's also important to notate? Good. The two groups are independent of each other. Okay, so now we are to large enough. And in this case, we do have both samples are the same size, so I think we can pretty much say 100 is greater than our 30 for both groups. And we are covered. Otherwise, if they were different sample sizes, we would write two lines and show that both samples are greater than 30. Okay. So, in conclusion, then, what's happening? Okay, good. Nearly normal. It's nearly normal, not normal model nearly applies. Nearly normal model applies. Okay, and before we go and start doing the rest of the problem, I have to just make sure you have a strong hold on what is in this normal model. Okay, so let's have this quick discussion. This normal model contains numbers, and those numbers represent the difference in the average weight loss of both groups okay? And you actually could probably shorten that and just say difference in the averages and then do this. I mean, this, you might actually even be able to get away with just notating that. So you have to label what is in this curve. This curve is the average of the low fat minus the average of the not low fat. So, question. If this difference is 0, what does that mean? That they're what? That they're equal. So let's say that Chance goes and takes a sample of 100 that were on the low-fat diet, and he puts them on the low-fat. He takes this sample, and he takes the other sample, and he finds that they are equal. Then the one number that he's going to get is going to be right here. That's the one number. The difference is that one number. Okay? Well, Becky goes and she gets another one, and she takes another sample of 100, puts them on the low fat, another sample and has them on the other diet, and she gets a number. It's up here. It is a difference that is positive. So if this difference is positive, what's it saying about these numbers? Good. When you subtracted, you got a positive number, so that means this average for the weight loss for the low fat was greater than the average weight loss for the other diet. Okay, but Cheyenne does her numbers and she gets something down here when she took 2 samples and got one number and subtracted it, and that one number was down here and it was a negative difference, so that means that what? Good. This number here, that second on the other diet, was the bigger number. That's why you got a negative difference. So actually, the other diet was a higher average of weight loss. Okay. So it's critical. You understand? One normal curve made up of the differences. Okay. So now let's do our problem. Part A, form and interpret a 95% confidence interval for the difference between the population mean weight losses for the 2 diets. So basically I need to do a panic model. The P and the A we just did on the front. So we are to name that interval. What do you think the name of this interval would be? How about a 2 sample? T what? Interval, good. Then what? For means. Do you know that on some of the quizzes, 23, I got people going, a 1 proportion t-test for means, or something like that. And I'm like, okay, so you're saying we have a proportion and a mean at the same time? Okay. All right. So here, the good thing is, the I is make your interval, and when you have 2 items, I let you do it in your calculator, so let's go to the calculator and talk about how to do that. Okay. Oh, somebody has my number 2 calculator. I don't know what class it is, but bring it back if that's you. You don't get to take my calculator. I only have like 5, 6 calculators, so don't take mine. Okay. So stat over to test. And so we have a whole big old menu, and let's talk about these first 4 tests. Okay, really important. Number 1 and 2, of course, happen when you have 1 sample. Number 3 and 4 happen when you have 2 samples. Why is there Z and T at the same time? What differentiates the use of a Z-test for a mean versus a T-test for a mean? Because these are all means. One uses a Z-score because we know it's normal, and how do we know that? What do they give us?
The sample standard deviation.
Okay, that's correct. One uses the sample standard deviation, which means the other one, they told us the what?
The population.
The population, the entire population standard deviation. How they got that, I don't know. That's why it rarely happens. Which one's which?
And the T-test where it's not, could be normal, but it's not
Correct.
normal.
Z-tests for means are if the standard deviation of the population is known. Okay, so you are allowed to use Z because that means it's perfectly normal if this sigma, which is the standard deviation of the population, is known. Okay, now then the flip side to that is you use a T-test if you only know the standard deviation of the sample. Okay, which is what happens most of the time. So that's why we mostly always use the T's for means. Okay, ta-da. So let's go down this menu. 1 through 4 are means. 5 and 6 are for proportions. 7 and 8 are intervals for, what do you think? Z and T test for what? Means or proportions? Nope, these are also for means. Basically, it has to say proportion to be for a proportion. Okay? That's pretty much straightforward. It has to say proportion to be for a proportion. So, are we going to do right now a Z interval, a T interval, a 2 sample Z interval, or a 2 sample T interval? That one. Okay, so this 2 sample T interval is the one we want, which is the 0. So there we go. Now, if you were using your own calculator, you've probably got something that looks like this. This is typically what pulls up. It's saying you got your data, and it has list 1 and list 2. Do we have data in list 1 and list 2 that we're going to use? No, we do not. You know what your problem would look like if you do that? It would look like this. See, you'd have data in a list 1 and a list 2. All right, but we do not. So we are going to then just put in our statistics that it gave us. So go over to stats, hit enter, and let's put in our data. So this top is the sample mean, the X bar, 9.3, standard deviation, 22.4, sample size 100. Next, group 2 has a mean of 7.4, a standard deviation of 16.3, and a sample size of 100. The confidence level the problem told us to do was 95% confident. Now, let's talk about this thing called pooled. You are always going to not pool. Never pool. It is way too cold outside to even think about going into a pool, so just don't do it. We are not part of the Polar Bear Club. We are stat cats, not polar bears or whatever. I don't know. So, no, do not pool. Sorry. There you go. Now, let me explain to you why. We're stat cats, not polar bears. Okay, here's why, if you're wondering why. Here's the reason. You are allowed to pull. You could be a little more accurate if your standard deviations were the same. So, meaning, if you had equal variance, then you could be a little more accurate in your estimation. But that would mean our standard deviations would have had to have been the same. Were our standard deviations the same? No. They rarely are the same. You rarely have the same standard deviations, so we pretty much don't pull. When you don't pull, it'll be a little more varied, and that's always safe. It's always safe to give yourself a little more leeway. So it's never wrong not to pull. So we're going to not pull ever. Do not pull. Okay, so there's the story about pulling. Don't pull, calculate, and here's your answer. It takes a while. It takes longer to find your number because it has to find the correct t distribution. Remember how there's a whole bunch of t curves? That's why you need to say to the reader which t curve was used, and I'm going to round up. Degrees of freedom will tell you which t curve was used. That's important because it's not the perfect normal z curve. They use the t curve. Now, I actually honestly don't know how they get this number right here because I'm like, a sample's 100, the other sample's 100. Where did 181 come from? So I've tried to figure it out, and I haven't gone into why that is. So we're just not going to worry about that. But we will write it down. You have to write it down. Otherwise, the person who's reading your test doesn't know which t distribution you use to make this computation. Yes?
So odd because the variance numbers are so the standard deviation.
Oh, no, because actually if I use the standard deviation, it comes out to be 193.
Oh, really?
Yeah. And I've even tried to see if it was Pythagorean theorem of statistics type idea, and it's not. So I don't know how you compute that. Okay. All right. So here we go. Now, yes, one more. Degrees of freedom is n minus 1. So see, we don't have 182 in our. I don't know. Okay. Now, I chose to go ahead and use those big numbers because I think it's very interesting that we have a negative number in our interval and a positive number in our interval. So I want to clarify and just make sure you truly understand what that interpretation is. Because if you can't interpret this properly, then who cares that you can come up with the numbers? If you don't know what they mean, it doesn't matter at all. Okay? Your business will not care about having you as an employee if you can't interpret what this means. All right, so first of all, we know we got this from taking the average of the low-fat diet sample we got and subtracting the average of the other diet. Okay, not sample, but that's an estimate for that population. So if this number is negative, then what's that implying? The average weight loss for this diet is 3.6 pounds higher, so it had more weight loss than the low-fat diet, the average of the low-fat diet group. Okay? Now, this number being positive means that what? The average of the low-fat diet is 7.4 pounds higher weight loss than the average of the other diet. Okay? You do not have to write this part that's in green. This is just me teaching you and making sure you have a strong foundational understanding of this, because you write stuff referencing this in your conclusion. So, here's how we're going to write our conclusion. I am 95% confident that the true difference in the averages, or average weight loss, of the two groups. Okay, so let me let you catch up right there. This is about the difference in the average weight loss, okay, of the two groups. That's important that it's actually phrased just like that. This is a number about the difference in the average weight loss between the two groups. Okay, and so I say that this number is from 3.6 pounds more for the no, or not the low-fat diet group, to, or up to, whatever you want to write that, up to what? 7.4 pounds more for the what? Low-fat diet group. That's how you write that. Okay, so do you see how this part that's in green, I don't have to write, but I have to know it because I put it in my interpretation. Now, what's also significant about this interval? What's so important and stands out in it? That what? 0 is in this interval. If 0 is in this interval somewhere, then that means that there actually could be what? No difference between the average weight loss. So we write that. These are the only ones, okay guys, these are the only ones that you have to include the 0 statement on. If there's 2 means or 2 proportions. Otherwise, it's not a difference, and so I'm not interested in 0. These are the only ones. If there's a difference, okay? So here, since 0 is in the interval, there could be, am I saying that there is no difference? No. Do not say there is no difference. That's like saying the null hypothesis is true, and you can't say that. There could be no difference in average weight loss. If you leave out the word average, it's wrong. Do you know that? That's crazy important. Did you know if you left out this, it's wrong? Because then it's as if you're saying just like a particular person's weight loss. Then it's, individualized. And this is about the average. This is a story about the average, not about individual weight loss. Okay? All right. Didn't you feel that the Brady Bunch song coming on there? This is a story about the average. Okay? Not about individual weight loss. Okay? All right. Now let's do our test. Here we go. I know, I'm sorry, my class is a musical, okay? It's just like I could sing, all the lines. Okay. Here we go. Now we test to see if there is a difference. Okay, so we've done the P, we need the H. We're doing the phantoms model. So what's the H? The hypothesis statement. What's the null hypothesis? That they are equal. Okay, in other words, no difference between them. What's the alternative? Oh, you need to go look at the front and read specifically what it says. So let's go over here. Let's see if we can't find. I think it says this. Do you see something else? I think it says the dietitian wishes to examine the effect this diet has on the weights of obese people. So is she saying one way or the other? No. Therefore, what do you think? Not equal to. It's to tell. She's not testing for more weight loss or anything. You might think that that's what she should do, but that's not the way it was stated. Okay? All right, so there's P, the H. We've done the A on the front, thank goodness. So we're to N. What is the name of this? Okay, 2 sample. T test. 4 means. Good. Okay, so we've done that. Let's see. Now we're to the T of the phantoms model. What's that? The test statistic. So that's your T-score or your Z-score. And so what is that? You know how we get it? Calculator. Yes, that's right. Let's go to the calculator. Okay? So stat, over to tests. What is it that we're doing? 1, 2, 3, or 4? I'm telling you, it's one of those. Number 4 is the 2-sample t-test for means. And yay, our data's already in there, so that's sweet. It carried it over from what we had entered in the interval settings. But please do make sure that you have the correct tailage going on down here. And that's a total made-up word. Don't use it regularly in anywhere else except for here. I'll know what you're talking about, okay? So cold is no. Burrs, too cold. No way, Jose. Calculate. And here we go. So let's talk about what these mean. An RT score is 0.686. What does that mean? Tell me what that means. What does a T-score of 0.686 mean? Okay, you say it's 0.686 standard deviations away from the mean. What's it? Close. That difference that we got. Correct. Right here, looking here, people, right here. Boom. The difference that we got one sample, and it was right here. Here it was. We got that particular sample and that particular sample, and the difference between those was only 0.686 standard deviations up. Okay, that's what that T-score is. And then, is that very rare? Oh no, that's even within 1 standard deviation. I mean, that's so not rare. So our p-value, according to our calculator, is what? How much? It's that 0.494. Very, very not strange. You must say what degrees of freedom is used. I need to look this up because I don't know if you need to round it or if you need to make it a whole number. I don't know. I need to look that up. But for now, it's, whatever. I'll probably take it either way for now. Because, and this is important, you can't leave this off. You have to tell the person which T-curve was used to compute these numbers, okay? All right. Let's see here. Oh, do you know what this p-value means? That was a chance. It was the chance we got our sample or something more extreme if the null is true. Yep. So basically, this is the p-value. Okay, so that wasn't rare at all. I mean, geez, it was almost 50% chance. Holy cow. Okay. All right. So now we are to obtain the p-value, which we already have, but we're going to compare it to alpha. 0.494 is way what? More than our alpha. So what conclusion do we draw? Fail to reject. We do not reject this. Now, am I saying that mu of L equals mu of N? No, I'm not saying they're equal. I just do not have evidence to reject their equality. So, question. Do you think that this decision coincides with the interval? Does that make sense based on the interval we had gotten up above?
Yes.
How so?
Zero.
Aha, very good. Because there was a 0 in here, there could be no difference. We already said that. There could be no difference. So since there could be no difference, I'm pretty much not going to have evidence to reject their equality. Okay? So it coincides. So see, that's another nice thing you have to rest your confidence in. Okay, so here we go. Finish this up. Since the p-value is not low, I fail to reject. And you would put this in words. That the average weight loss on the low diet equals the average weight loss on the other diet. Yes?
So if there's 0 in here, there's no chance of
If there's a 0 in the interval, I'm probably not going to be rejecting. I can't say there's no chance that if you're like right on the edge, if that interval is right on the edge of 0, it could be, depending on the confidence level, you might end up rejecting it and what alpha they give you and stuff. And if that's the case, then you would say, you know, I might need to double check this because I'm getting varying conclusions in between my interval and my test. That's true. Yes?
So when you're writing it, would you say that the average of one equals the other one? Or would you say...
Yeah, you can say I cannot reject this, that this could be true. Say that this could be true. That this could equal that average. Okay? So, do I have evidence? Let's answer the question she asked. This lady, or this dietitian, whoever it is, man, woman, whatever, wishes to examine if this diet has an effect. Does this diet have an effect? We do not have evidence it does. So we do not have evidence that this low-fat diet has an effect, because that's what the question specifically asked, on what?
All of these.
Average. If you don't have this in here, wrong. This is a story about the average weight loss, not about an individual person's weight loss. Okay? Story about the average weight loss. I'm sorry it sounds silly, but you know what? That's what is going on here. Weight loss of obese people. Okay?
All of these.
Okay. All right. Ta-da. Okay, so make sure when you take a look here, yep, I'm going to give you that. Be aware that you're probably going to have to be drawing 2 histograms. You do finish this assignment. There's 4 problems, but you don't do panic and phantoms on all of them. Okay, you're not doing panic and phantoms on all of them. I just took you through that. Okay, good job. Now I'm going to come and stamp you for what you did on Friday.